All right. Okay, so thanks for the introduction. My name is Justin Petucci. I'm a staff member over at the Institute for Computational and Data Sciences, and as a member of the scientific consulting team. And today I will be touching on some of the capabilities of the CTSI Informatics core in terms of supporting research that leverages electronic health records through the digital Collaboratory for precision health research, as Dr. Hanavar mentioned. I'll be touching on some sort of similar topics that Dr. Hanavar touched on in terms of Odyssey and TriNetX, and sort of offering some additional details of just different information in terms of how you can get started using that data. And then I will touch on one of our pilot studies with actually Dr. Aziz's group, taking a look at different health outcomes for COVID-19 patients that had some pre-existing conditions. So with that, probably not needed now, given the introductions, but I will offer a little motivation. So as we know, many fields across domains are currently in a situation where vast amounts of data exists, and this data has the potential to be useful and perhaps transformative in terms of the wealth of information it contains. Healthcare is no different, right, with the abundance of EHR and claims data. And really the challenge is sort of, there's many challenges in realizing the potential of that data, right? As we heard a few times, simply getting access to that data of data of high quality and quantity can be a challenge, right? This is healthcare data. I come from a sort of computational physics backgrounds. So whenever I think of healthcare data in my mind, I just see brick walls everywhere. And I feel like there's a lot of barriers to getting access to healthcare data. In addition to that, once you have the data, having the expertise to, quote unquote, wrangle that data, right, clean that data, get it into a structure that can be easily ingested into an analysis pipeline, right? That takes a particular skill set and a particular set of expertise. Having expertise in your group to run different data analysis methods, whether that's statistical or machine learning, whether you're trying to answer a clinical characterization question or do some sort of predictive modeling, right? That all takes expertise that maybe your group doesn't have. Simply having the technical ability to go through that pipeline in a computationally efficient way, right? So some of these medical data sets are terabytes in size. So it's not something, as Dr. Hanavar mentioned, not something that you can easily read into a pandas data frame on your, or an R data frame on your local machine, right? You need to have computational infrastructure that can, handle data sets of that size. And again, that takes another layer of expertise. So what we're trying to do in the informatics core within CTSI is sort of aiming to help address some of these different challenges and sort of make life easier for the researcher who, has a clinical question and maybe doesn't have the expertise in all these different areas. So with that said, goals for today, I'll touch on some methods to get access to EHR data, EMR data, available now to the general Penn State researcher, discuss different ways the informatics core can help with some of those key challenges. And then, as I mentioned, I'll showcase one of our pilot studies that utilize some TriNetX data. So again, Dr. Hanavar touched on Penn State's instance of the OMOP common data model. So this came out of a public-private project in collaboration with the FDA and some private funding from pharmaceutical companies, and the NIH sort of administered this project. So it was an initiative to sort of standardize observational health data, and one of the key outcomes was a defined structure for observational health data known as the OMOP common data model. So Penn State has an instance of this running in a sort of test environment. And right now, sort of in the process of getting that moved over to a production environment. So as of 2021, this was had patient records for 1.8 million patients. And again, this is EHR data. So, taking a look at patients' history longitudinally through the Penn State healthcare system, quantities such as different diagnoses that patient has that has been recorded in their medical history, different medications, different labs, vital signs, so sort of all that's available for these 1.8 million patients by sort of leveraging, again, right, there's different ways to store healthcare data. And as it's been mentioned, the primary purpose of EHR was, intended for billing purposes. The OMOP common data models sort of, its intention is to use that data for research purposes. So by formatting our data in this way, we can immediately take advantage of some very nice command line tools and graphical user interfaces that can readily sort of build cohorts and run analyses directly on this data. So it's sort of taking that data, putting it in a new form that's, being rapidly adopted by many different healthcare organizations out there. So, for example, if you're interested in patients with COVID-19 that have a pre-existing peripheral artery disease, right, you can build a cohort using the graphical user interface, run some analysis directly on using some of these tools available through this OMOP common data model format. So one key challenge, aside from getting access to data, is getting access to data of sufficient quality and quantity. So, right, this was alluded to a few times. What are your options if Penn State Health's data just simply isn't enough? Maybe the clinical question that you're after, you build a cohort using our data and, you only have 10 patients. What can you do? And sort of enter Odyssey. And again, Dr. Honavar touched on this. So the observational health and data science and informatics community formed out of the OMOP project, with the goal of empowering a community to collaborate and generate evidence that promotes better health decisions and care. So they provide, outside of this common data model, different methodologies and also open source software that sort of supports that mission and vision. And these numbers are hot off the press as of their monthly or yearly conference that took place last month. So in terms of the numbers, you can see there's collaborators that have their healthcare data formatted in this OMOP common data model format in 80 different countries, 3,000 plus collaborators across the globe. And sort of the huge statistic here is they have patient records for 12% of the world population. And being at that conference, this is sort of their lower bound estimate for how much data is now formatted using this OMOP common data model. So sort of what does that mean for you as someone who wants to sort of tap into that, 12% of the world population data? So as Dr. Honavar mentioned, the sort of position of Odyssey is to get around sharing that healthcare data. So every site has their data standardized in terms of its format, and you share code, and each site runs that code, and then sort of the study leader aggregates the results of that code. So you're no longer dealing with sort of all the challenges of sharing data. You're simply writing a general pipeline or a general analysis protocol and sharing that with each site that wants to participate in that particular study. So using Penn State Health's current OMOP CDM and test sort of status, we have participated in a single study, and this was a clinical characterization study out of Columbia University, and it's in the process of being submitted for publication now. As we move to production, we have the intention of participating in a lot more of these community studies that come out of Odyssey, and we also have our sights set on leading our own multi-site study, as Dr. Honavar mentioned, right? If we have a clinical collaborator that has a relevant sort of question that we can help sort of design that protocol and help recruit different sites, again, to tap into that massive amount of data that's there. Maybe we won't be able to get every site to study, but we can certainly expand on what's available here at Penn State Health. So switching gears, aside from Odyssey, how else can we get access to more EHR data? TriNetX is another one. So this is, again, completely separate from Odyssey, and it's available. Reach out to one of us in the CTSI Informatics core, and we can help get you set up. But essentially, this comes to you through a web interface. Dr. Honover had a couple nice screenshots. There's several different networks available. You can see here that the research network has over 1 million patients, records for over 1 million patients. The Diamond network, which is exclusively claims data, has over 200 million patients available. So essentially, you log in, you can build cohorts, right? You have some definition of sort of qualifiers that sort of defines your cohort. And from there, you click a button and you can request to download that cohort and then go off and do your analysis elsewhere. Or you can directly do some analysis in the TriNetX web platform. And that's sort of currently in the process of being expanded, and they're working to sort of build this cloud platform where sort of it's a one-stop shop to doing different sort of analyses on cohorts that are built with their web platform. So what's available in TriNetX, again, it's de-identified healthcare data, very similar to what you would get from the Odyssey community, right? Patient diagnosis codes, medications, procedures, vital signs, demographics, those sorts of quantities are sort of what would be at your disposal. So summarizing, what can CTSI Informatics Core do to help you, the researcher who's interested, right? So I mentioned a few times accessing the data. We have our own instance of OMOP, which will be moving to production. We can get you set up for TriNetX, or we can, again, help sort of partner with you to define that protocol and potentially lead a multi-site study through Odyssey. Through the successful completion of several pilot studies with our clinical collaborators, such as Dr. Aziz, we now have sort of a statistical pipeline in place that sort of runs the traditional data science or machine learning pipeline, from data access to cleaning and feature engineering to building a model, training that model, and then testing it and interrogating that model. So we can help with that entire process. I mentioned that TriNetX and Odyssey community have their own sets of open source tools. We can help sort of train in that area. Really, if you're a clinical collaborator and you have the expertise that certainly I don't have as a computational physicist, and really you have a clinical question and sort of you can bring that to us, we'd be happy to collaborate and offer this defined pipeline that we have, right? We have software in place. We have access to high performance computing systems through the Institute for Computational and Data Sciences. And also there's a high performance computing system directly at Penn State Health that we can leverage, right? We have all the software and environments in place to grab the data, immediately sort of ingest and clean that and run through different analytic pipelines. So I should mention that we're not limited to just EHR data that we would extract from TriNetX or Odyssey, right? Some groups, such as Dr. Aziz, there's other databases that exist out there that maybe were designed for research purposes, which would be, happy to collaborate with as well. So that sort of ends my spiel for, what can we do in terms of helping the Penn State researcher take advantage of EHR data. Now I want to just quickly dive into one of our pilot studies. So this particular pilot study utilized data extracted from TriNetX, and we were looking to predict 30-day clinical outcomes for COVID-19 positive patients, both with and without a pre-existing condition, peripheral artery disease. Some of the goals, we wanted to just sort of find the best performing machine learning predictive model and compare that to a traditional classical statistical model, logistic regression. We wanted to start to get at what features are important to this model and maybe start to tease out, investigating that relationship between the input features and the output prediction. So just taking a look at this general prediction level, patient level prediction framework. So we have some target population. In our case, that was COVID-19 positive patients with or without PAD. We're aiming to predict what patients at a defined moment of time will experience some outcome during some time at risk. So for us, our time at risk was 30 days, and our index date was the date that the patient had COVID-19 in their EHR record. So this is the traditional patient level prediction framework. It's applicable to many different prediction problems, and this is the framework that we used for this study. Here's a summary of our features. Again, these are heavily sort of informed by our clinical collaborators. So sort of what are potential important features to include in the model: age, race, some pre-existing conditions like hypertension, diabetes, smoking, etc. These are the sort of a summary of the outcomes that we investigated. So mortality, ventilation, hospitalization, stroke, heart attack, and we have our sort of summary statistics for our different groups. So COVID-19 with PAD and without. And this slide summarizes the comparison between logistic regression, so our classical sort of statistical approach, and then the machine learning approach. And here we're sort of comparing the model performance for all of our different outcomes, and our metric of comparison is the AUROC, so area under the receiver operator curve. And so what we can see from this generally, similar performance with the machine learning model, which is a gradient boosted decision tree classifier. Marginal improvement for most of the clinical outcomes, but for the most part, very similar performance. So this tells us that the assumptions made in applying the logistic regression model in terms of linearity and feature interactions, not so far off, right? So the machine learning model has the ability to capture feature interactions and nonlinearities, and the fact that the performance isn't, massively better than logistic regression tells us that those assumptions, aren't really violated, right? There's not that much signal that logistic regression is missing. This slide summarizes some of the significant outcomes for the PAD groups, so those patients with the pre-existing condition of PAD. So you can see for, in general, we're across the different outcomes. Here I'm showing odds ratios, and in general, again, we see decent comparison between the XGBoost model and the logistic regression model. So general agreement. And we see for all of these different outcomes, we have an odds ratio larger than 1. So this pre-existing condition of PAD sort of increases the odds of these outcomes, right? So people with PAD are more likely to be hospitalized, have stroke and heart attack as compared to the general COVID-19 population. The last slide I'll share here is sort of getting at the question of what features are important to our predictive models. So here, there's many ways to attempt to elicit that information from a predictive model. Here, I'm plotting something known as Shapley values. And here, I'm just showing sort of on the left, the top 9 features in terms of prediction to that model. So we see age, was the patient a smoker? What was their race? Did they take aspirin medication, etc.? So from this, we get a list of features that are important, which could, maybe the clinical collaborators can start to think about and maybe generate hypotheses. We're not sort of attempting anything sort of causal here, just associations. So these features are important, and also we can get a sense of how these features are impacting the model. And so for example, if we hone in on smoking here, smoking in our data set was a binary variable, so 0 or 1, 0 indicating that the patient had no history of smoking in their medical records, 1 meaning they did. So in terms of the color coding here, smoking is blue, non-smoking is blue, and smoking is red. So we see people who smoked have a Shapley value, if we look at this vertical 0 line, that's positive, and people who don't smoke have a negative Shapley value. So this means that smoking causes an increase in probability of the positive class here, so increases the probability of this hospitalization outcome. So people who smoke are more likely to be predicted to be hospitalized within 30 days. If we look at race, so race white is one of our race features. So sort of the opposite trend. People who have race white are less likely to be hospitalized. Again, so from this, we can start to tease out these different, how do these input features impact prediction values, and that's something that's definitely sort of an important phase beyond prediction. What's important to the model, and trying to get at the question why. So with that, I'll wrap up. This is sort of a graphical summary of what I talked about. Essentially, the informatics core has EHR data available to you, whether that's through our instance of OMOP CDM, whether that's through a multi-site study through the Odyssey community, or through ChinaX, or maybe you're bringing your own data. We have expertise in different analytic pipelines. We have software and compute infrastructure to help take that clinical question that you may have and realize some type of study. And with that, I will wrap up, and thanks for your time. If you have any questions that may not be addressed and maybe we don't have time for in the Q&A, feel free to reach out to myself, or if you want access to some of these data resources, I have some contact emails there.